Okay, we're going to continue on where we lectured last time online. Nice to see everybody in person again. We are continuing on here, chapter 2. So last time we talked about, again, how to properly take measurements, how to count significant figures. So remember, sort of the rules for significant figures is as follows. Pretty much any non-zero is a significant figure. And that's really important as well. It's also sort of where we start counting our significant figures. So remember, we always kind of start left to right on the number, and we don't start counting really our sort of significant figures until we hit the very first non-zero that's present. Then there's zeros, speaking of zeros. And there's three types of zeros that we talked about. There are leading zeros. And these are really all the zeros that come before you hit that very first non-zero number, and those are not significant. So you can have as many as you want. As long as they come before that very first non-zero, they will not be significant. There's trap zeros or captive zeros, and those are significant. And these are zeros that are between two non-zero numbers. So like 4004, those would be significant. Up here, something like this, those guys would not be significant in that case. Then we have really the trailing zeros. And those may be significant. And they're significant if there's a decimal point in the number. So remember, that's really the defining sort of factor as to whether the zeros that come at the end are going to be significant or not. Is there a decimal point really anywhere in the number? As we talked about, it does not need to be like right next to the zeros or anything like that, as long as it's in the number somewhere. When you're counting significant figures in these zeros, in terms of that decimal point, it does need to be written in order for it to count for significant figures. We just don't assume it's there. So again, if it's not written, then it's not there. So it does have to definitely be sort of written. So if we had something like, again, I think we looked at 600 like that, technically speaking, one significant figure. If we put 600 like that, now all three of them would be significant. If we had something like this, these would not be significant. We would start counting here, significant, and once again, these three at the end would be significant because of that decimal point I just covered up right there, would be in the particular number. So that's the deal with the zeros at the end. We also talked about if we write a number in scientific notation, all those numbers that come before the times 10 part are always going to be significant. And scientific notation sometimes is a really good way to write a number with a certain number of significant figures, because you can kind of control how many significant figures you write, basically. And as we also talked about, sometimes that is the only way that you could actually get a number to the proper number of significant figures. So just happened like 15 minutes ago, somebody came up with this as their answer, and they wanted two significant figures or needed two significant figures based on the calculation. And there's no way to get two significant figures and keep it at 2000. So again, the only way that you would be able to do that, 1, 2, and 3, would be to actually write in scientific notation. That would maintain the two significant figures that you would need for the calculation, and also not change the meaning of the number. So remember, we wouldn't want to do like a 20 on this, right? Because 20 and 2000 is very different in terms of their numbers or values that they mean. Speaking of calculations, we also talked about when we do calculations, what we should end up with our significant figures. And there's really sort of two categories, I guess, of calculations that we do. We typically will either multiply or divide. And when we multiply or divide the number of significant figures in the answer should equal the significant figures with the least number of sig figs in your calculation. So your answer should have the same number of significant figures as the one with the least number of significant figures. in your calculation. So if we took 3.20 and times it by 1.2, in terms of significant figures, that is 3 significant figures, that is 2 significant figures. So our answers should end up with 2 significant figures when we would calculate it. The other sort of category of stuff that we do is we could add or subtract. And when we add or subtract, we're actually looking at decimal places. And it is the smallest number of decimal places. Is how many decimal places, again, your answer should have, not significant figures. So that's very times confused by people when they add or subtract. They still think it's got to be significant figures, but it is decimal places, not significant figures. So if we had, again, 1.24 plus 3.0, 424, that is 2 decimal places. That is 1 decimal place, which means we really should end it right there at 4.2. Has 1 decimal place, but again, it has 2 significant figures, which might be important if you're going to take that number and continue on to do a calculation with it. I think we also talked about if you do multiple sort of calculations together, you really should try to avoid rounding to the end, and you should just keep track of your significant figures. So if we were going to do something like this, we would do what's in the parentheses first, and we're multiplying. So this has 3 significant figures. This has 2 significant figures. That means technically when we get the answer, we should have 2 significant figures up on top. Personally, I probably wouldn't round at that point because I know I'm going to take that number now and divide by the bottom number, but I would want to keep track of that. And then I would divide by the bottom number, which has 4 significant figures. That means in this case, we should end up with 2 significant figures based really on the top one. Again, I probably wouldn't round to the very end and kind of clean it up at that point. Any questions on any of that stuff we talked about, I think, last time? Okay. Then let's continue on. Inequalities. So with the metric system, there's a lot of prefixes that are used. And we will definitely use prefixes, and we want to make sure that we understand sort of how to do them correctly. So for example, kilo is a prefix, and kilo, 1 kilometer is 1,000 meters. Milli is a prefix. 1 millimeter is 0.001 meters. So there's a table we'll see and a table in your book, and very often what you'll see sort of in those tables, for example, is something like kilo, and it'll say something like 10 to the 3. And we want to make sure that we use it correctly. And it's a very common mistake that people will always sort of do this conversion incorrectly. So first off, 10 to the 3 is really, if you needed to put in your calculator, it's really 1 times 10 to the 3, basically in scientific notation is essentially what that is. So when you see this, like kilo is 10 to the 3, or milli, for example, is 10 to the minus 3, that is how much there is in the base unit to one of the prefix units. So for example, in 1 kilometer, which would be the prefix unit, right? The base unit here would be meters. That would mean that there are 10 to the 3 meters, right? And 1 times 10 to the 3 is 1,000, by the way. So that's where that number comes from. Does it matter the base unit? It doesn't. So, 1 kiloliter would be 10 to the 3 liters, right? 1 kilogram would be 10 to the 3 grams. And that is the proper way to use those. These are equalities, which are basically 2 units on different scales, but represents the same amount of something. What I say about using it correctly is most of the time, or a lot of the time when people go to this table or try to use this sort of conversion, they will oftentimes write something like there's 10 to the 3 kilometers in 1 meter. And then again, that is sort of the backwards use of it. So when you see that 10 to the 3, 10 to the minus 3, we'll see a table here in just a second with the rest of them. What you see on that table is how much there is in the base unit, again, to one of the prefix units. So don't get it backwards. Very common people sort of do that. So here is again, as I was just mentioning, it really doesn't matter what the base unit is. The prefix is the prefix. So it's the same conversion regardless if you're talking about meters, if you're talking about liters, if you're talking about grams, it doesn't really matter. It's the same sort of conversion. So each of these, again, is 10 to the 3 meters, 10 to the 3 liters, 10 to the 3 grams. So sometimes people think, well, oh, I'm talking about grams, meters, liters, maybe it's different. It isn't. Again, it's the same prefix, it's the same conversion, regardless of what that base unit really is. So here's a table from your book of some of those things. And this is the sort of scientific notation version of it. And for these different sort of prefixes, tera, giga, probably not going to see too much of that, I don't think. Mega pops in occasionally, but kilo definitely we see a lot of in this class. Again, there's that 10 to the 3, which is really 1 times 10 to the 3. Here's some other ones that are common: deci, centi, milli, micro, nano, pico. So a lot of these do pop up in chemistry. I would say for our class, again, probably centi, milli, micro pops up a good amount. So those are some of those things. So once again, if we were talking about micrograms, this is the sort of abbreviation there for micrograms. But in your textbook, they use this as the abbreviation. So if you see that, it's really a microgram, which is really, that's a true symbol. Maybe they didn't have that font when they wrote the textbook. They've actually made that font. So if you see that, that is micrograms, sort of symbol, if you will. The real symbol anywhere else is basically that symbol right there. I'm not really sure why they did that too much, but they will sort of do that and use that in this book. So speaking of that, if we had micro, and again, we look on it and it says 10 to the minus 6. So what that means again is if I had 1 microgram, which is the prefix unit, there would be 10 to the minus 6 grams, which is the base unit. So again, that is the proper way to use that. Now, you could also, for example, if we look at centi here, which is 10 to the minus 2. Let's go back maybe a page here. Whoops. So we have centi, which is 10 to the minus 2. So 1 centimeter, which is the prefix unit, would be 10 to the minus 2 meters. Now, sometimes you will see there are 100 centimeters in 1 meter, which is also a perfectly fine conversion, perfectly fine equality. We get that by dividing both sides by 1 times 10 to the minus 2. So if you take basically 1 divided by 1 times 10 to the minus 2, you get 100, and that's the sort of bigger whole number sort of conversion between those two. And you can use that as perfectly fine. You could use the other one, which is 1 centimeter is equal to 10 to the minus 2 meters. Thank you very much. So let's talk about doing some conversions or something, or using the sort of property to do some conversions. So let's say, for example, I had 425 centimeters, and I want to know how many meters that was. So what do we do with these equalities? And we'll talk a little more about it as we continue through this chapter, but why not preview it since we have it here? We could really grab an equality, and again, it's up to you in this case which equality you want to use. But regardless of the equality, which are what these two things are, and actually we'll use this guy here, top guy. This is our equality, and we really can right? What is sometimes referred to as conversion factors. And we can write two conversion factors from any equality like that. And conversion factors really are just fractions where you say, for example, 1 centimeter over 10 to the minus 2 meters, or 10 to the minus 2 meters over 1 centimeter. So these are what are referred to as conversion factors. And the reason we use conversion factors, as we'll talk about for the rest of this chapter, pretty much when we do calculations, we do what is referred to as dimensional analysis, which is we set up the calculation so that we could clearly see the units and see what units cancel each other out and what units you're left with. So when you how they want you to show you is through this approach where we grab a conversion factor and we use it to really get rid of the units we don't want, and we are left hopefully with the units that we do want. So how would we do this? For example, here we would take something like the 425 centimeters, and we know we want to go to meters. So 425 centimeters is really not written as a fraction, but it is assumed that that's kind of like over 1, if you will. And basically what that means is in terms of the units that we want to get rid of, the units are up on top. And when we do dimensional analysis, essentially all we're going to be doing is multiplying and dividing. And basically when we do this type of calculation, the one thing that you have to remember is simply opposites cancel. So if you want to get rid of a particular unit, you need to put that same unit in the opposite location. So if we look at it here, centimeters here are on top. And when we go to our conversion factor, the one on the left, the one on the right has centimeters on the opposite location, which is the bottom. Which one is that? That one is the one on the one on the right has the centimeters in the opposite location, right? It's on the bottom. So we would set this up like so. And normally you don't put the 1 on the bottom there, but you can if it helps you. We're going to put 1 centimeter on the bottom, basically 1 times 10 to the minus 2 meters on top. What this is essentially doing, and let's just talk mathematically what we're doing here. Mathematically what we're doing is we're going to take whatever is on top and we're going to multiply. So whatever there's on the top gets multiplied. And then we're going to come back through and divide by whatever's on the bottom in this particular case. So what happens with the units in this case is because there's a centimeters on top and a centimeters on the bottom, they cancel out. And it's the same idea as if you took 2 divided by 2, that equals 1, right? They essentially cancel each other out. So if you have a unit of centimeters on top and a unit of centimeters on the bottom, it's like dividing 2 by 2, it equals 1, which essentially means they cancel each other out. So when we do calculations and you want to get rid of units, what you want to do is always think opposite and not lose where you were, I suppose. So in this particular case, what we would do is we would take 425, we would times it by 1 times 10 to the minus 2. Make sure you use your exponent button, obviously. And you will end up with 4.25. The only unit that's left is meters, which is up on top. So we basically took 425 times 1 times 10 to the minus 2. I didn't really do it because everything on the bottom is 1, so there's really nothing to divide by, but you can, you'll get the same number, obviously, if you divide it by 1. And that is, how we would convert, for example, from centimeters to meters. We could, again, like I said before, use the other sort of version of this conversion factor where we have this. And we could write 2 conversion factors for this guy, which would be 100 centimeters over 1 meter, or 1 meter over 100 centimeters. And again, just to show if you chose that version of it, it will work out the same. We would set it up the same way, 425 centimeters. Once again, we're going to use the one in the opposite location. 1 meter up on top, 100 centimeters on the bottom. We're going to cancel out the centimeters since they're in the opposite location. We're going to multiply here. if you want, don't really need to. Then we're going to come back and divide by the 100 on the bottom. So we're going to take basically 425 divided by 100, and we will end up with our 4.25 meters. So this shows you if you want to use the other one, obviously it works the same way basically because it's a legitimate conversion. Question on that there. Okay, so why don't you try one maybe? Why don't we do let's do let's see, we have 2,325 micrograms. How many grams is that? So why don't you take a second, try to set it up with the conversion factors. There's our micro right there. Yes. And see what you come up with. Okay, so let's take a look. So first off, we would go to our table here. We see, as we just talked about there, that micro is 10 to the minus 6, which is here. And again, that is 1 times 10 to the minus 6. From that, we can get our equality, which should be in 1 microgram. There is 10 to the minus 6 grams. So once again, in one of the prefix units to that much of the base unit. That will technically give us 2 conversion factors. We could say in 1 microgram up on top, there are 10 to the minus 6 grams. Or we could flip it around, basically 10 to the minus 6 grams is 1 microgram. So those are, again, the 2 conversion factors that we could use to do this problem. So we'll do it here. We'll go with our 2,325 micrograms. Once again, micrograms, although not written as a fraction, is up on top because it's basically over 1, which means to get rid of it, again, all you have to remember is opposites. Don't make it too confusing, just go opposite. And we'll use this as our conversion factor here. 10 to the minus 6 grams is 1 microgram. Once again, here we're going to multiply what's on top and come back and divide by what's on the bottom. Not much to divide there again on the bottom since it's just 1. But the units on top and the units on the bottom will cancel each other out. Once again, we would go 2,325. We would times it by 1 times 10 to the minus 6. Again, making sure you use your exponent button. And you will end up with 0.002325 grams. First off, any questions on that setup there? Significant figure wise, right? I think we talked about exact numbers as well, maybe the other day. This is basically a definition, and that's considered an exact number, which means significant figure wise, that is where we should look, which is 4 significant figures. So our conversion here still has 4 significant figures. You could also write in scientific notation if you wanted to as well. You would need to keep all the numbers in that case, right? So you would have something like 2.325 times 10 to the minus 3. So you would have to keep all those numbers to keep the proper number of significant figures. Questions on that there? All right, so let's say, which is a very common thing that sometimes people try to do, but maybe not so successfully, or they try to figure out, all right, going from like this prefix to this prefix, I'm gonna kind of move some decimal places over. Maybe there's a song or something. I can't remember the song right now, how to do it or any of those things. So what if we had to go from one prefix to the next? So let's just say, for example, we had 63,585 micrograms, and we wanted to know how many milligrams that would be. So kind of like a prefix to prefix sort of movement. So we would probably want to grab our 2 prefixes here. And what I would recommend when we're doing this, and actually, let me just go to the page, maybe I got a little bit more room to write. So I got 63,585. So I'm going prefix to prefix, and sometimes people are like, well, I'm gonna try to figure out how to do that in like a one-step move. And I would highly recommend perhaps not doing that because most people screw it up. They don't do the right sort of movement one way or the other. So what would be the easier move? Well, the easier move would be, obviously we have a table like this that you probably could reference. And using this type of table, it would probably be very easy to figure out how to go from the first prefix back to the base unit, kind of like what we just did, right? So you could very easily find how to take it from the first prefix unit to the base unit. Then you could also very easily find from the base unit to the next prefix unit conversion as well. And that's how I would probably recommend to do it. Do it maybe a multiple step type thing, and you won't screw up perhaps moving things. Besides, you do need to show your work, so just moving zeros. And if you move the zeros wrong, you might not get credit. So in this case, we have two prefixes we really want to look at. So we have our micro that we were using there, which is still 10 to the minus 6. And we also have our milli prefix. And again, if you go to that table, milli will be 10 to the minus 3. So those are the two things that you could always find on that table, right? You don't have to try to look at the table and go, I don't see one that goes from like micrograms directly to milligrams, right? So knowing that these prefix ones from the table take you back to the base unit, that's a really good approach. So our approach here would be, let's take it from the first prefix unit to the base unit, which is grams, right? So we'll go from our prefix to our base unit. And then we can take it from the base unit to the next prefix unit. And once again, we're able to very easily find the conversions to do that without trying to figure out, how to do it all in one step, right? So if we take this approach, we're going to do the same deal. We're going to make sure we use these correctly. So in this case, that would mean that in 1 microgram, there is 10 to the minus 6 grams. That would also mean in 1 milligram, there is 10 to the minus 3 grams. So those are the two equalities, and the proper way to use that, once again, it is not 10 to the minus 3 milligrams in 1 gram. So don't get it backwards. This is going to give us really two conversion factors for each of these equalities. We could say in the first case, if we were to write the two conversion factors, 1 microgram over 10 to the minus 6 grams, like we saw previously, are 10 to the minus 6 grams over 1 microgram. For our other guy right here, we could have 1 milligram over 10 to the minus 3 grams, are 10 to the minus 3 grams over 1 milligram. So we got our equalities. It's going to get us there. We have our pathway to get us there. We are not going to, as we'll continue to talk about throughout the rest of this chapter, we're not going to use all these conversion factors. We're just going to use whichever ones we need to get rid of the units we don't want and sort of leave us with the units that we do want. So we're going to start with the number here that was given to us, which is 63,585. And once again, we want to kind of set it up like this dimensional analysis. And again, not really written like that, but that helps us. And maybe if it helps you to do it, you can. It will orient you to see, again, micrograms there are on top. So the first move we want to go is from micrograms back to the base unit. That's going to be one of these two conversions. Should I use the conversion here on the left or the one on the right? I do need to use the one on the right. That puts the micrograms in the opposite location of where it's at. That means on the bottom should go 1 microgram. Up on top should go 10 to the minus 6 grams. If I stop my calculation right at this point, the units I am in are what units? I am in grams because up on top is a microgram, which will divide out the micrograms on the bottom. And the only unit that's left is what I'm almost want at this point, which is grams, right? This is also really important to set it up like this because now I could clearly just see the units of grams are up on top, which means to get rid of them, I need to put them on the right. So I can use conversion factor on the left or right on the bottom there. I need to use the one on the left, again, opposites. So the benefit to doing this, besides the fact that's the way you need to do it, is it will make the math part a lot easier if you just think opposites, right? And you could clearly see where things are. And we would just continue on with our calculation here. Again, we're going to put the grams on the bottom. So we're going from here to here now. And we're going 10 to the minus 3 grams is 1 milligram. Once again, I have grams on top. That's going to divide out the grams on the bottom. The only unit left at this point is milligrams, which is what I'm looking for, right? I'm looking for milligrams. By the way, if you are solving for 1 unit, like we are here, the unit should end up on top or bottom? Top, yeah. So if you always have 1 unit, it should always end up on top by itself, yeah. If you have 2 units, which you could have, you might have top and bottom, but if you have 1 unit, you want to end up on top. This is also why it's good to set it up like this, because if you see your milligrams are on the bottom, you didn't really solve it correctly. You did something backwards, right? So you got to keep those things in mind. All right, so math, what we're going to do here is this. We're going to multiply whatever's on top there. So we're going to go here and multiply. And again, if you want to, you can do the 1, but you again don't have to. When you're done multiplying the top, you should hit the equal sign. And then you're going to come back and divide by what's on the bottom. Really don't need to do the 1 because, again, it won't do much. But if you want, you can. You should hit equals if you do that. Then you're going to divide by the next one on the bottom and hit equals. So if you have multiple numbers, which you really don't in this case, but if you have multiple numbers on the bottom, there are actual numbers other than 1. You should divide by each one individually, hit equals after each one, and you will always get the right answer. If you try to punch it all in at once, good shot, you're not going to get the right answer. Yeah. So let's do that. Once again, that's going to be here. I trust you. So I'm going to punch it in anyway. So at 63,585, we're going to multiply it. Remember that 10 to the minus 6 is 1 times 10 to the minus 6. So again, 1 exponent button, negative button, minus 6 when you put it in your calculator. It equals divided by, again, the 10 to the minus 3 on the bottom is 1 times 10 to the minus 3. So 1 exponent button, minus 3. Yeah. And negative, 3 there on the bottom. All right. And if you do all that, as was correctly said, I think 63.585 milligrams would be our answer in this case. So I see it all the time. People try to go from like one prefix to the next, and they're like banging their head on the wall going, what is like this to this prefix? Don't do that. Just take it back to the base unit. You'll have that table probably available to you. And it just makes it a lot easier. You can find those conversions a lot easier. Just do the extra calculation and you'll probably get the right answer. Any questions on that? All right, so probably will show up somewhere, be given to you like kilo is 10 to the 3 or centi is 10 to the minus 3. I'm sorry, centi is 10 to the minus 2. You just need to know how to use it properly. So make sure again that you know how to use it properly. Any questions on any of that there? All right. All right. So let's take a look at some of these. We got 1,000 meters, and we got 1 times 10 to the minus 6. So we'll take a look at some of these that we just saw. So 1,000 meters is equal to 1 kilometer, right? That is basically the kilo conversion. 1 times 10 to the minus 6, that is our micro that we were just using. And again, that is the same as what we see on that table as 10 to the minus 6. So that's the same deal. And 0.1 liter is deciliter there in that case. Yeah. What's up? Oh, okay. All right. So let's talk about some equalities. And again, I would say we will come across this one a lot. And again, you can use this version of it if you like, or you can use the 10 to the minus 2 version of it. I would say also probably this one. Not too much of that probably outside of looking at a ruler maybe, but I guess that's good to know. I think we talked about when we were talking about rulers, right? That is what you see on the bottom of a ruler typically, right? On the top of a ruler, inches usually, centimeters, the numbers, and the smaller guys are millimeters, right, that you typically see on a ruler. There we go. So here are some common equalities for volume. Once again, whoops, get back. This is definitely one that we use the most, I would say, and very often. So just knowing that one, just make your life a lot easier. 1,000 milliliters is a liter. I would say in a lot of cases, we record volume in milliliters very often, but a lot of times when we use it in formulas and stuff like that, it has to be in liters. So converting from milliliters to liters is like something that we do a lot in chemistry. So like I said, to make your life easier, I would remember that conversion because you'll use it probably a lot as we go through the different chapters. Deciliter and all that kind of stuff, we don't see too much of it. Liters, milliliters, really your big two, along with this, which is a cubic centimeter, which is also a volume. So one way that you can get a volume is taking length times width times height. And if you measure again each of these in centimeters, which are all length measurements, but if you multiply them together, you will get a volume measurement of cubic centimeters. And that's a very common way that you can find the volume of like a solid square object or cube like that. And that is also a volume unit that's used a lot. A really important conversion is 1 milliliter is the same, or it's a 1-to-1 conversion between that and a cubic centimeter. So it's basically a 1-to-1 conversion between that. In medicine, cc is sometimes used for a cubic centimeter, like give the guy 5 cc's of this before they die or something, right? So it's really a milliliter. So occasionally in medicine, you see it written as a cc, which is still a cubic centimeter. So this relationship also, along with the 1,000 milliliters is 1 liter. Those are, I would say, two really important sort of volume equalities that we do come across a lot in chemistry. And there's the cubic centimeter in a syringe, for example. And again, that is 1 liter, right? And you would do the same thing, by the way, on this scale as any other piece of equipment. You would count how many markings, right, there are between those things. So that's like 5 markings between 1 milliliter. So that's like 2.2, right? 2.4, 2.6, 2.8, and 3. Each of those lines represent. So the best you could do on this guy would be a whole number, not really a whole number, but to the first decimal place in this particular case. Now, mass, some very common equalities we have in mass. I would say definitely probably these guys right here are the ones that we do see a lot. 1 kilogram is 1,000 grams, and 1 gram is 1,000 milligrams. So once again, those two are very, very commonly used in chemistry. Not too much centigrams in the most case, and that type of thing. So I would say those two are very common. The balance that you use to weigh out mass, again, usually gives it to you in grams, and sometimes we do measure things in milligrams, and in medicine sometimes they use kilograms a lot when they weigh people and record things like that as well. All right, identify, let's take a look at these. Each of the larger units, millimeter or centimeter is centimeter, kilogram, centigram, deciliter, microliter. And that is micrograms. I'm still getting used to seeing it written like that. Micrograms are milligrams. Milligrams, yes, would be our larger one in each of those cases. All right, so with 1,000 meters equals how many? What do we got to go in there? Should be a kilometer. Sounds good. And 0.01 meters is a centimeter, right? That's 10 to the minus 2. Basically, if you're not sure, you could just move this way, right? 1, 2, 10 to the minus 2. By the way, if you move this one this way, 1, 2, 3, right? 10 to the 3, right? So that is those conversions that we saw on that page. And I could do that because what we see on the page, again, is the base unit in each of those cases, right? So that's how we kind of match it up. All right, complete each of these. 1 kilogram is 1,000. Sounds good. And 0.01 centiliters would be. So it would be 0.01 liters, right? There. So again, centi is 10 to the minus 2, right? So again, that would be in 1 centiliter. There is 10 to the minus 2 liters, right? In the base unit. I guess I should write like that. 1 centiliter is 10 to the minus 2 liters. Gives us this conversion or this conversion. So we were starting with centiliters on top. We would want to use it like this. And 1 centiliter is 10 to the minus 2 liters. Those will cancel. And again, if you take your 0.0 minus 2, we should get, hopefully, I think it's missing a 0. Did it have the 3 zeros there? 0.0001, I think, is what it should be. That looks the same as what it started with, I think, yeah. So I'm going to say they should probably have an extra 0 there would be good. So you should have 0.0001 liters in this case, should be the proper one. Yeah. What's that? Truthfully, probably not. In terms of volume, really milliliters and liters are your kind of 2 big volume units that you use most of the time, I would say. Outside of chapter 2, where you probably will come across a lot of the different units because it's about conversions and stuff like that. But outside of chapter 2, we get into real chemistry. I don't know, it's real chemistry there too. But in real sort of normal chemistry type formats and stuff like that, milliliters and liters are really the 2 big units that you see. All right, kind of like I think we talked about temperature, right? And like we had the degrees Fahrenheit, degrees Celsius, and Kelvin. Outside of the chapter with temperature, most chemistry involves taking temperature measurements in like degrees Celsius and then convert it to Kelvin. Those are kind of the 2 that you see in most cases. Very similar. All right, so we kind of jumped the gun, but we'll officially talk here about writing conversion factors. And again, conversion factors are really used, as we were doing in some of those problems, to set up your calculation and to really get rid of units that you don't want and end with units that you do want. It's really sort of a fraction sort of thing. And we can write conversion factors for any type of equality. And if you remember, there's sort of 3 types of equalities that you could come across. You could have the sort of English to English conversions. You could also have metric to metric conversions. And you could usually have as well ones that cross over from metric to English type of conversions. So that's what we sort of see in some of these. That's metric, a little English, and a little crossover event there. So it doesn't really matter sort of the type of equality that you have. They do represent the same thing. So for each of these things, we could write 2 conversion factors. We could write 1 meter on top, 1,000 millimeters on the bottom, or 1,000 millimeters over 1 meter. For the second one, we could write 1 pound up on top, 16 ounces on the bottom, or we could flip it around and use 16 ounces on top and 1 pound on the bottom. And for our bottom one there, 2.2 pounds over 1 kilogram, or 1 kilogram over 2.2 pounds. So when we use these conversion factors, some of them are considered exact numbers and some of them are not really considered exact numbers. And the importance of that is when we do calculations and try to figure out how many significant figures we should end up with, We only look at things that are not exact numbers, really more measured numbers. So we'll talk about this again a few slides down the road, I think here, but if you're doing a metric conversion or a English to English conversion, you could pretty much ignore those. Those are considered exact numbers. But when you do cross over from English to metric, you do have to kind of look at the numbers that would be there. And we'll take a look at that in just a second. But basically, you would have something like this on the bottom. The number in terms of significant figures you would look at is the actual number. So usually what you'll have when you have that crossover, or in really any sort of conversion in most cases, is you'll have one of the numbers is actually the number 1. And then the other number is an actual number like 2.20 that we see there. So if we were to use this one in a conversion or a problem that we're calculating, we would want to take the 2.20 into account in terms of 3 significant figures. We would not look at the 1 part of it because you'll always end up with 1 significant figure if you did that. So when you kind of cross over metric to English, you want to look at the one that's the actual number in terms of your significant figures. This guy here, you don't have to worry about it. You really don't have to worry about it with that because, again, it's a metric to metric or English to English type of thing, conversion. So obviously on food labels, we see both. We see sort of English measurements, and usually in parentheses, we have some of the sort of measurements there. And sometimes when you're baking and stuff like that, right, they give it to you like you need this many kilograms or milligrams of this or that, right? And sometimes it's a little bit different. Now, equalities with significant figures, as I mentioned before, if you stick to metric or English to English, consider an exact number. Once again, an exact number is found one of 2 ways. It is something that is counted, or is something that's considered a definition like this, sort of an equality. And what the deal is with exact numbers is they tend to have really an unlimited number of significant figures. They could really be in as many significant figures as you want. And because of that, people ignore it when they're using these in calculations, because I may say I want to use 3 and you may say you want to use 4, and then technically speaking we're both right because they could have as many as you want. So to rule that out, when you come across a exact number in a calculation, you just ignore it and you move on to whatever else is not an exact number. So 1 gram, 1,000 milligrams would be 1 foot and 12 inches, and 1 minute is 60 seconds. And remember that some things will not be provided for you, right? So again, in terms of time, right, there is, again, 60 seconds in a minute, right? 60 minutes in an hour, and only 24 hours in a day. Yeah, so not 60. So that might not be provided for you. Here are some that are metric and English, and we do need to look at these when we use these. So for each of these, we could write a conversion factor. We could write 454 grams over 1 pound. Our 1 pound is 454 grams. This would be 946 milliliters over 1 quart. Our 1 quart is 946 milliliters. And obviously we could do the same thing for the last one there. When we go to count significant figures using these conversions, we again want to look at the actual one that's a number. So we would look at the 454 here, and it would count as 3 significant figures. We would look at the 946 here, and it would count as 3 significant figures. So what do I mean by this? Let's just say we had 12 milliliters, and we wanted to know how many quarts that was. So why don't you do the conversion, set it up like we were just doing with the conversion factors, set it up with the dimensional analysis, and give your answer to what you think the proper answer should be based on significant figures. Okay, so let's take a look. So once again, we just want to think about, like we were doing before, we want a pathway to get us from milliliters to quarts. By the way, sometimes there may be more than one pathway to get you there in a conversion. Obviously, this one seems like a good one since it's sitting right in front of us. And we wrote our two conversion factors, obviously, that we can use from that. So we will start with what was given to us, which is 12 milliliters. Really, the milliliters are up on top, right? So to get rid of them, the conversion factor on the left or right should be used. It is the one on the right. That will put the milliliters once again in the opposite location. So again, it's not written, but it basically is up there on top. That would mean we take 946 milliliters and 1 quart. Milliliters divided by milliliters will cancel out. In this case, we're going to multiply, not really necessary since it's 1. We're going to then come back and divide by what's on the bottom here. So we're going to basically take 12 divided by 946. And that's going to get us on our calculator this number here, I think, 0.012684989 units or quarts. Clearly, that's a lot of significant figures there. We are multiplying and dividing here. And one of the nice things about dimensional analysis is when you set it up like this, that's all you're doing is multiplying and dividing, which means when we follow our significant figures rule, we are following our number of sig figs is what we're looking at, right? So we know for sure we should look at the 12 here, which has 2 significant figures. Do I need to look at this conversion factor? I do, because it is a metric to English conversion. So I do need to actually look at this. The number, once again, that I want to look at is not the 1, but the actual number. And this would count as 3 significant figures, which means really my answer should end up with how many significant figures? Should end up with 2, which means we should end up right here. That looks like a 6 to me, which means I should then round it up, right? And we should end up with this. Now, I won't say 100% of the time, but frankly, a lot of times, but not 100% of the time, you should still look at it. But a lot of times, even in a situation where you do need to look at the significant figures of that, a lot of times it's still like that first number. If you're just doing a conversion, oftentimes pretty close to where it should be, but it can happen. So, I mean, if we started with, say, 1,224 milliliters, right? That would have 4 significant figures, and this would then have 3 significant figures. Then our answer would have to come to 3 significant figures. So it can happen. You should look at it. Once again, if it is a metric to English conversion, you need to do that. The one that you do not have to worry about metric to English is this one right here. 1 inch is exactly 2.54 centimeters. So even though that is an English to metric conversion, is considered an exact conversion and you would ignore it. But everybody else there, all 3 of those on the screen there above, along with the 2.2 pounds in a kilogram, that one that we saw earlier, also you should look at it. So certain conversion factors that come from equalities you don't have to worry about. But when you do cross over and that kind of looks like a metric to English type of conversion, you probably should look at it. Any questions on that? Yeah. We get 2 significant figures because math-wise, what we did up here, mathematically, what we did was basically 2 things. We multiplied and we divided. And when we talked about the rules for significant figures, when you multiply or divide, you want to look at the number of significant figures and all the numbers that you multiplied or divided. And whichever one had the least number of significant figures is what your answer should have. So in this case, we really only had 2 numbers we had to look at. Obviously, the one's really not there, and the one over there we wouldn't look at. So it's really just looking at these 2 numbers here, and one had 2 and the other one had 3. Yeah. Mm-hmm. Yeah, so if you had, say, let's just say, for example, we had, I'll just make up some numbers, 4,233 centimeters, and we want to know how many inches, right? So we would use this as our conversion factor. We would take our 4,233 centimeters. Once again, we could write our conversion factors as 1 inch over 2.54 centimeters are 2.54 centimeters over 1 inch. So in this case here, we would want centimeters on the bottom, which would be 2.54 centimeters is 1 inch. So we would take 4233 divided by 2.54 will give us 1666.535433. This is obviously what's on my calculator. Centimeters would cancel. Now, when we go to look at this, because this guy right here is considered an exact conversion, we just ignore it. We ignore any type of significant figures there are. You don't round it. You will round now. The conversion factor we ignore, but we still have one other number, right? And the other number is the original number. And that's the number that we would have to look at. So in this case, we would have to go to the only other number that's there, which is this one. And we would have to look at it, which in this case has 4 significant figures, which means we actually should round to 4 significant figures. And with that 5 there, it means we actually should round up, right? And we would end up properly here at 1667 inches. So if you come across an exact conversion as a conversion factor, you just ignore it, but there should always be at least one number, at least the first number you start with, as a number that you should look at for significant figures. Yeah. Because most of the time, if you're doing some type of conversion, that first number is probably what's considered a measured number, and you should look at it. And I would say probably 9 times out of 10, all your conversion factors are probably going to fall mostly in the, it's an exact number, you don't have to worry about it. So that's what I was saying earlier. A lot of times you get all those exact numbers in the middle. So a lot of times you're just not really going back to that first number a lot of times as looking at the numbers in the figures. Yeah. Yeah, if our original number is just 33. Yeah, yes, that would be 2 significant figures. Again, you wouldn't look at the conversion factor because this one is considered an exact number. Other questions? All right. Now, same idea. If this guy, like I said before, was a larger number, we do need to look at this guy, and that would be the one that would determine it in that case. All right, so conversion factors, sort of talked about this, have been doing it. Again, is really nothing more than a fraction, and we're just going to use it to help us set up everything correctly and cancel out what we don't need and keep what we do want. So no matter what equality you have, you should always have the ability to write 2 conversion factors from it. And as you've seen in some of these examples we've been doing, you won't use them both or all of them. You're just going to use whichever one you need to kind of get you to where you're going. So here, obviously, 1 hour is 60 minutes. We could say 60 minutes over 1 hour. Our 1 hour is 60 minutes. Here are some equalities, and these are our metric to metrics. So as we've been talking about, if you pull any of these equalities from this row of the table or column of the table, and these are all English to English or US to US conversions, or if you pull anybody from that column of the period of this table here, those are all going to be considered exact. So if you use any conversion factors that come from those, you really don't have to worry about them in terms of significant figures in your calculations. And if those are the only type of conversion factors you use in that calculation, pretty much just go back to the original number, and that will be the significant figures that you need. If you pull from this sort of column where we're crossing over from metric to US, that is the column where you do need to look at the numbers that are in there, except for this one, right, which is considered an exact. So once again, when you would go down this column to look or use them to count significant figures, you would always want to look at the actual number, not the one part of it. So that guy would have 3. This guy would have 3. This guy would have 3, 3, 3, and so forth all the way down. This guy would have 1, right? That would have 3, 3. So you want to look always at the number part of that if you had to, and not the one part of it. So don't worry about it here. Do a little bit of worrying over here if those guys pop in there. Any questions on that there? Yeah. Yeah, pretty much that's like that's the big given of exact, like on a ruler, you go straight down 2.54 centimeters is basically what you get. The only other one I've pretty much ever seen that sometimes people will use, I won't say that, but that sometimes people will use as an exact conversion, and you want it in your case is the one with grams and the very last one there, grams and pounds. The real number is 453.6 grams equals 1 pound. If you use technically 453.6, that is an exact conversion. But most books nowadays will use the 454, which is not really exact. So it falls back into you should look at it. But that 1 inch to 0.54 centimeters is the only one that you have to worry about in terms of it being exact. No, so time's the same. It's really the same units, right? It's hours and stuff like that. Yeah, I hope so. Well, no, I hope no. Yeah, 1 minute is exactly 60. I thought you said an hour. Yeah, but 1 minute it would be 60 seconds. Yeah. You wouldn't worry about the significant figures in it at all. So I wouldn't look at it as 60 is 8. You wouldn't. And the way it's written, it actually would have one significant figure since there's no decimal point written on it. Yeah. But you wouldn't look at it. So, like I said, anything that you pull really from this column here or this column here, don't even worry about it. Let us continue on. So, in addition to obviously whether to ignore these conversions or equalities or not ignore them in terms of their significant figures, this is a good reference table that you might need along the way. But some of these ones, we do use sort of a lot, like I mentioned before. We do definitely see kilometers and meters. We also, the milliliters and liters are cubic centimeters, grams, and so forth there. Hopefully we know those, right? That 5,280 feet is a mile, comes up a lot. And obviously, bless you, miles to kilometers and milliliters to quarts, and definitely, I would say probably this one a lot as well. Not that none of the other ones might not pop up, but those are some very common ones that we do use. So let's talk again, look at some of these conversion factors as we've been writing. We got our 1 meter is 100 centimeters. So again, our two conversion factors, which are really just fractions, 1 centimeter on top and 1 meter on the bottom, are 1 meter on top, 100 centimeters on the bottom. This is our kilograms to 2.2 pounds. This again would get us our two conversion factors. Do I need to look at these in terms of significant figures? Both of them, none of them, only one of them? Which one? If I was doing the calculations, do I need to worry about significant figures in either of these two? The answer is yes, this one. Yes, that is your English to metric conversion. So you would have to look once again at this number as you're doing your calculation. This is a straight metric to metric, which would fall into the exact number. So you do not have to worry about that guy if you were using that as a conversion factor. All right, so let's take a look at some of these equalities here. I think a lot of them we kind of went through. So 1 liter is 1,000 milliliters. Once again, our two conversion factors. So this is our equality. And these are obviously our conversion factors. And again, in this case, is there any one of these here that I would have to worry about? The answer is yes. And it is. Which one do you think it would be? It would be B, yeah. So that's an English there to metric or US to metric. So we would have to look at that. Top one is metric, metric. Bottom one there, metric to metric. We don't really have to worry about it on those two, but the guy in the middle we would. So why is it important to sort of work these problems out like we were talking about with what's really known as dimensional analysis and showing these units? It's really because You do need to show these units where we have, whatever unit A to unit A go to unit B, and they cancel out, and you can clearly see it. Now, when people really don't set up their problems like this, and they do what I sometimes call stacking, where this, sort of like stack numbers and keep stacking numbers this way, or just rando numbers all over the page. Maybe there's units, maybe there's not units. People really screw up the calculation a lot because you don't know if you're supposed to be multiplying, not sure if you're supposed to be dividing, you're not sure where certain units are. Most common sort of error that happens when people really don't set it up, with this dimensional analysis approach where you can see the units is, like, speaking of time, the people always end up multiplying when they should be dividing by like the 60s, or they divide when they should be multiplying by the 60s. So just setting it up like this where you can see the units, again, just makes the math part something you really don't have to think about, because you could just look at it and go, oh, everything on top I multiply, everything on the bottom I divide. Units are opposites of each other. Who cares about anything else? The other thing about setting things up this way is, frankly, sometimes in formulas, you won't even need to worry about formulas sometimes, because you just think about the units you want to get rid of and the units you want, and it will kind of do the formula for you. And it'll do the math of the formula or rearranging a formula for you by setting up the units so that they properly cancel and you're left with what you need. So down the road, when we start incorporating some formulas, sometimes just taking a more dimensional analysis approach where you kind of get rid of units that you don't want, keep the stuff that you do want, it will kind of make the rearranging of formulas a lot easier in terms of the math part of it, by setting it up this way. So I highly, highly recommend that you do that. Not really a recommendation, because if you want all the points, that's the way you need to do it. But it is beneficial for a lot of things down the road as we kind of go through it. Now, sometimes we do get some conversion factors from the actual problem itself, and we do need to use those in the problem. So, for example, a car travels at 85 kilometers per hour. By the way, when you have something in words, like you are driving 65 miles per hour, those are two different units, right? So when somebody says miles per hour, that means you went 65 miles in 1 hour, basically, right? Or in 1 hour, you went 65 miles. If you did like miles per hour, right? If you were driving that. If you were driving 85 kilometers per hour, that means you went 85 kilometers in an hour, or in 1 hour, you did 85 kilometers. When you get conversion factors that actually come from the problem itself, you do have to look at the significant figures, because that's not a true exact conversion, right? Maybe this time you're driving 85 kilometers an hour, maybe next time you're doing 185 kilometers per hour, whatever it may be. Of conversion that's specific to the problem, and you use it as a conversion factor, you do have to look at it. Same sort of rules apply. You're going to look here at the 85 and not the other number, obviously, which is a 1, and that would count as two significant figures. So, by the way, if we had, say, we'll come back here to our little conversion list here, right? Let's say we are doing our, I'll leave it up here so you can use it. Let's say we did have 85 kilometers per hour. Yeah. How many miles per second would that be? All right, there's the conversions. See what you come up with. See if you come up with that. I'll do it too, because hey, I just made it up. Hopefully we'll end up in the same spot. Okay, so let's take a look. So we really have two conversions we need to do, right? We need to take the top part there to miles, right? And we need to take the bottom part there to seconds. This is really where dimensional analysis is really helpful to keep us focused on where's each unit located and what we should do mathematically with it. So there could be multiple pathways to get you to the answer depending on what conversion you use. But I see here personally, this looks like a direct pathway that's going to take me from kilometers to miles, right? That I can use to fix the top part of it. That will give us two conversion factors, right? That will give us 1 kilometer over 0.621 miles, Or we could flip it around the other way, 0.621 miles gives us 1 kilometer. Now on the bottom, there are multiple ways you could do it, but if you just want to kind of go step by step, we could take hours first to maybe minutes, right? And minutes to seconds, right? That will get us there. Or if you know the conversion between hours and seconds, you could go directly there, right? It's whichever way you want to do it. So we can find those, by the way, here, as it's both, whichever column you want that from. We got the here and here. And that obviously gives us two conversions. 1 hour is 60 minutes, or 60 minutes over 1 hour. And we have 1 minute over 60 seconds, or 60 seconds over 1 minute. All right, so now we got our sort of pathway. We got our conversion factors. We want to set it up with our units and dimensional analysis. So here's what we want to do. I'm going to erase this so I got somewhere to write. All right. So this is how I'm going to, actually, maybe I'll write a little smaller up there so I can fit it in. We're going to take it as 85. We had kilometers, right? Per hour, right? And I'm going to write it exactly like that, where I could clearly see my kilometers are up on top, right? My hours are on the bottom. Now, as long as I set it up like this and use my conversion factors like we were doing previously, all I have to remember is opposites, right? So I'm going to start with just the top conversion. And I want to take my kilometers to miles. I do want my miles to end up on top as well, right? So it don't really matter about that. We want to go opposites. So kilometers are up on top. I should use the conversion here, top or bottom here on the right. That is both answers, but I'll go with the louder one, which is that one right there. It's going to put my kilometers in the opposite location. So that's what I would want to do with this conversion right here. We will take it and we're going to set it up. So opposite on the bottom, which would be 1 kilometer. Up on top would be 0.621 miles, basically, right? If I stop my calculation right at this point, what units cancel? What units am I left with right at this point? Miles on top per hours on the bottom, right? I have now successfully finished the top part, right? Nothing more to do on the top. The benefit of setting up like this, I can again clearly see my hours are where, which means when I want to get rid of my hours, I need to put them on top, right? I don't have to think about where to do it, right? It's just like opposite. So that will take me to my first set of conversions, and that's going to put my hours up on top, right? Which would be that guy there. And we're going to continue on. You could get an answer if you want to, but I'm just going to kind of continue on with the calculation here. I'm going to put my hours on top, which is opposite, and my 60 minutes on the bottom. At this point, the hours on the bottom and the hours on top should cancel out. If I stopped right here, the units I am in are what units? Miles per minute, right? Which is close to what I want, but I want miles per second. So I need to continue. Added benefit of this is I don't have to think about it too hard. Minutes are on the bottom, which means to get rid of them, I need to put them on top opposite, right? So I'm going to grab the appropriate conversion factor and not drop everything on the floor. And I'm going to put my minutes on top, which actually will be the one on the left here as well, right? And I'm going to do that. And we'll go with 1 minute, 60 seconds. At this point, minutes on top, minutes on the bottom cancel. The units I am now left with are miles per, which is what I want, right? So just thinking opposites, lining my units up correctly, even if I got multiple units to deal with, just take one at a time, go opposite to cancel. First off, any question on that setup there? Now, what are we going to do mathematically here? Everything that's on top is going to get multiplied. Yeah, so we're going to multiply. Don't really have room to put the arrows, I think, but we're going to multiply everything on top. And by the way, when we get to the end there, we're going to hit equals. So Then we're going to come back and divide by what's on the bottom and then hit equals, and then divide one more time by what's on the bottom and hit equals. So if I'm going to punch this into my calculator, I want to make sure I'm going to get the right answer, which might be a good thing, I'm assuming. I'm going to take 85. I'm going to multiply it by 0.621. Essentially, that's the only two numbers there, right? Everything else is a 1, which means if you multiply by 1, nothing changes. I'm going to hit equals. That finishes my top part. I'm going to go to the bottom. The very first one there is a 1. I don't really have to worry about it. The next number is 60. I'm going to divide by 60 and hit equals. The next number is another 60, which means I'm going to divide by the second 60 and hit equals. And now you should have the correct answer 100% of the time if you punch it in that way. If you try to punch it all in together and don't put parentheses correctly, you will get the wrong answer. You'll probably do the math wrong. So you want to make sure you punch it in. Now, in terms of my answer on my calculator, I got me 0.00146625. The units still stay are miles over seconds. Typically, when you do this, the number stays with the top unit and the bottom unit is 1. Yeah, so you don't really put a number on the bottom. Is that good sig figs? That's a good answer. That's not good sig figs. So now we got a bunch of conversion factors. We have our original guy as well. We want to think about what do we have to look at in our calculations, right? So we're going to start at the right and go backwards. So we'll start with this conversion factor here. Do I need to worry about it? I do not. It's considered an exact number, so don't need to worry. How about the one next to it? No, it's considered exact. How about this one? Yes is right. There it is. There. So yes is right. This has how many significant figures? It does have 3 based off of that number, right? How about our original number? Do I need to worry about? I do. How many significant figures? 2 based off of that number. Answer should have 2. Again, all we did is multiply or divide, so we're looking at significant figures. That puts me here, right? I should round up, yeah? And a little miles per second action, yeah? Any question on any part of that there? Felt like we jumped ahead a little. It's all right. It all comes together at the end, I suppose. So this is a really good illustration. Sometimes people really freak out when there's multiple units and they got to do conversions of both units. And again, setting it up like this almost makes it kind of like a no-brainer if you just remember opposites. So you just like don't have to worry about it. And all you have to remember second to that is once you have it all set up, anything on top multiply, anything on the bottom divide. So not much to worry about in terms of the math part of it either. So it makes it a lot easier. I would say probably 80% of people, if they want to go do this problem and did not set it up like this, would be multiplying by the 60s at the end there and not dividing and not really sure where things are. So it's a very common, maybe some of you did that, I don't know. But it's a very common mistake that people make. So you want to get in the habit of setting these problems up like this. It just makes the math easier. You don't have to worry about it. And just like opposites always cancel math, basically. That's how they should just teach math. Opposites cancel, right? Do the opposite thing to get rid of it. Any questions on that one there? Okay. All right, so let's go back to looking at that. So as we were talking about here, it is very common in problems that you are given information that you should look at the significant figures. This obviously would be a situation like that. Same thing here, a tablet contains 500 milligrams of vitamin C. You write 2 conversion factors, 500 milligrams of vitamin C over 1 tablet, or 1 tablet has 500 milligrams of vitamin C. Here we would look at the significant figures. And by the way, written like this, it has, as it says there, 1 significant figure, right? There is no decimal point written on that 500. So it has only 1 significant figure. That's probably good because you probably want to give a person 1.325 bits of a tablet, right? You'd either give them 1 or 2, probably, I imagine. Maybe 1.5 if you, most of them say don't break the thing in half, right? Another very common thing that we're given in problems is percentages. And a lot of times we do want to convert these percentages into really usable sort of conversion factors like we might have talked about there in chapter 1. Again, the easiest way to sort of make a percentage into a usable conversion factor is to assume 100 of whatever you have. It just keeps the numbers the same. So here, if we have 18% body fat by mass, if we kind of take a metric root, that means you have 18 kilograms of body fat over 100 kilograms of body mass, or you could flip it around the other way. You could also do a more English or US conversion and say you have 18 pounds of body fat per 100 pounds of body mass, right? So that's the same percentage. And it's the kind of same idea. If you got 95 on your exam, you probably got 95 points out of 100, right? So by assuming 100, it keeps the number that the percentage is the same, and you don't have to do more calculations. So we obviously would look at this as well when we're doing it. We would not look at the 100 part of it. We would look at the 18 part of it in this case in terms of the significant figures, and it would have 2. Here is Keflex. There we go. Antibiotic, 250 milligram capsules. That means that there are 250 milligrams of Keflex in one capsule, or one capsule has 250 milligrams. Here we would look at it again as a measured number, and we would look at the 250. And again, the way the 250 is written, no decimal point there at the end. So just the 2 and the 5 are going to be significant here, and it would count as 2 significant figures in your calculation. All right, so let's take a look at some of these equalities here that we could write. Meters to decimeters. 1 meter is 10 decimeters, and that will give us 10 decimeters over 1 meter, or 1 meter over 10 decimeters. A jewelry contains 18% gold. So again, assuming 100 grams, that means you got about 18 grams of gold for every 100 grams of jewelry that you have there. Or if you flip it around, 100 grams of jewelry for every 18 grams of gold. 1 gallon of gas, yes. Where's that? $2.40. It's probably expensive when they wrote this book, I imagine. I have one on one of my slides. It was like $3.09, and it was really expensive back then. I would love that right about now. That'd be it. But $2.40, you know, this book was written a long time ago. So that basically means you get $2.40 gives you 1 gallon. Not in this state, but 1 gallon over 240 cents. Maybe like Tennessee. I was down there. There was like $2 and some odd cents. Told the people, like, we pay like $6. They're like, whoa, $6. Jeez. All right. Let's talk about problem solving, which we have sort of been doing. Again, set up your stuff. It is referred to as dimensional analysis or problem solving, and it is that unit-based way of showing your work. And it is very helpful outside of conversions as well. It can just really help you with formulas as well and kind of getting the math correctly. So when we do problems, there's a few steps that you can follow that can be helpful. A lot of times you want to write what's given to you, and that goes for any type of problem. Sometimes, especially if you have formulas, for example, if you write what's given to you, oftentimes you can look at what's given to you and go, that looks very much like this formula. And you can figure out what you don't have, and it'll help you sort of figure out how to do it. You want to think about a plan, which way will get you from one unit to the next. As I mentioned before, there are multiple pathways depending on sort of the conversions you choose to get there. As long as you choose legitimate conversions, not ones you made up, you know, it should give you the same answer at the end as you go through it. You want to get your conversion factors and obviously set it up so that we see the units canceling. All right, so why don't we try some of this here? Person weighs 178 pounds. What is it in kilograms? Once again, there's 2.20 pounds in 1 kilogram. So set it up and see what you come up with here. Most of it will probably be provided for you. There might be some that you do need to memorize. There's those review sheets that are up there on Canvas for the exams. And if it says technically on there, like, hey, you should know this one, it may not be provided for you. So I think maybe like the 1 inch is 2.54 centimeters is on there or something like that. But I would say probably a majority of it will be up there. You just need to make sure you use it correctly. Again, except for maybe something like hours and minutes and that type of stuff. So hopefully we know those guys. The review The review sheet is not really problems or anything like that, but there are some worksheets that are problems. But there's actually a review, like a review sheet that tells you pretty detailed of like from this chapter. This is like all the stuff you need to know and stuff like that. All right, so let's take a look at this. We want our pathway to go from pounds to kilograms. Clearly, this is going to get us there in one move. We could write our two conversion factors of 2.20 pounds over a kilogram. Our 1 kilogram is 2.20 pounds. And we're going to start with our number that was given to us, 178 pounds. Once again, not really written as a fraction, but that pounds is up on top, which is important because now all I need to do is opposite, right? So that is my opposite move. And that's going to give me 1 kilogram up on top, 2.2 pounds on the bottom. The pounds will cancel. We're basically going to multiply on the top there, which is not much. So it's basically 178. We're going to come back and divide by what's on the bottom, the 2.2. This is going to give me 80.909091 kilograms. Now, in terms of significant figures, do I need to worry about this one? That is correct. So this one has 3. Do I need to worry about this number? Yes, this one has 3. And that means the answer should probably have, that's not a bad one. That's right about there, yeah. And that next number is a 0, so that's an 80.9 kilograms, yeah. Any questions on that one there? Yeah. And again, basically multiplying and dividing. All right. That's hopefully what they came up with. That's good. All right. All right. We got rattlesnake's 2.44 meters. How many centimeters long is the rattlesnake? There's 100 centimeters in one. All right. So on this one, we could use obviously meters to centimeters. You could also use the other version of it that we saw in that table. Again, they both should get you to the same endpoint there. We're going to write our conversion factors, 100 centimeters over 1 meter. Our 1 meter is 100 centimeters. You chose this one, 1 centimeter over 10 to the minus 2 meters, which is 1 times 10 to the minus 2, right, on your calculator. Our 10 to the minus 2 meters is 1 centimeter. So using this here, again, 2.44 meters. Meters are up on top, so to get rid of it, we're going to go meters on the bottom, which should be that one, or if you chose that one, whichever one you did, will give us our 100 centimeters is our 1 meter. Those will cancel. We're going to multiply here, not much to divide on the bottom since it's 1. So we're going to take 2.44, we're going to times it by 100, and give us 244 centimeters. Now, in terms of significant figures, do I need to worry about this one? I do not, because that's a metric to metric, so we're good on that. That's an exact number. That means we do have to worry about this number, right, that has 3, and we should end up here, obviously, with 3 as well. Any questions on that? All right. All right, so let's take a look at this one. A doctor orders a prescribed doses of 0.15 milligrams. If you only have a 50 microgram tablet, how many tablets do you need to give? So why don't you give that a go? Again, milli is 10 to the minus 3. And micrograms are micro. It's micro, which is this guy, is our 10 to the minus 6 that we saw earlier. All right, so take a moment and see what you come up with. Okay, let's take a look and see how you're doing. So in this case, we do have actually a conversion factor given to us in the problem, and that is, as it showed there in that table on the bottom, we have a 50 microgram per tablet, basically. So basically what that means is there are 50 micrograms of this medicine in every 1 tablet that you would take, or we could use it in the opposite way. In a tablet, there is 50 micrograms, right? Now we're going to use that really to go from the sort of doses, if you will, to how many tablets we need to give the person. We have a problem though in terms of our units, because Our doses there is in milligrams, right? And our tablets, though, are in micrograms. So we cannot use them together the way they are. We have to actually do a conversion. You could either convert the milligrams to micrograms, which is probably the easier move, I would imagine, or not. I don't know. We'll see. Or you can convert the micrograms to milligrams in the conversion factor. So whichever way you want to do it, they should give you the same. I'm going to take the milligrams and I'm going to convert them to micrograms. And again, that will allow me to use this conversion factor the way it sort of is. I am going to do what we talked about earlier today, which is I'm not going to try to bang my head on the ground and try to figure out how to directly do that. As I could clearly see from my table, I could find the conversion that will take me from milligrams to the base unit of grams. And then I can use that to go from the base unit of grams to the next prefix one. And again, that is my 10 to the minus 3. And then my 10 to the minus 6. So again, that's going to probably be a much easier route in the end because you'll get the right answer probably. Yeah. And you know, you hopefully won't screw up the conversion. So that's where we're going to start. We're just going to use them as conversion factors. Once again, a reminder that this would mean in one of the prefix units, which is milligrams, there is 10 to the minus 3 grams, right? That is the proper way to use that number as the equality. And that will give us two conversion factors of 1 milligram over 10 to the minus 3 grams, or 10 to the minus 3 grams over 1 milligram. While we're here, we'll do this guy as well. That means in 1 microgram, there is 10 to the minus 6 grams. And again, that's the proper way to use that equality. That will give us our other options of conversion factors, 1 microgram over 10 to the minus 6 grams, or 10 to the minus 6 grams over 1 microgram. Any questions so far? All right, so I'm going to still set this up with dimensional analysis so I can see the units and not have to worry about too much. So I'm going to take my milligram doses there of 0.15 milligrams. And again, milligrams are up on top, which means to get rid of them, we're going to go opposite, which means we do want to use a conversion factor like that, which will give us 10 to the minus 3 grams over 1 milligram. At this point, if I stop my calculation, I'm in units of grams, right? That's close to what I want, but I do need to go to micrograms. Benefit of this, there is no confusion. Grams are on top or bottom. Yeah, you can clearly see they're up on top, right? And that's going to help me with the next part of it, which is I got to get rid of grams. So lo and behold, I'm going to take grams on the bottom. I didn't even really think about what I'm doing, but I just know that's opposite. So that's going to get me to the right spot. That will give me 10 to the minus 6 grams is 1 microgram. Grams on top, grams on the bottom will cancel. The only unit left standing, micrograms, and it's on top, which is what we need, right? When we're just solving for one unit by itself. Any questions on that there? Once again, we're going to multiply basically this 1 times 10 to the minus 3. We're going to come back basically and divide by that guy there. So if we do that, we will take 0.150 times 1 times 10 to the minus 3 and hit equals. We will then divide it by really the only number on the bottom, which is 1 times 10 to the minus 6. We want to make sure we're using our exponent button, obviously. So divide by 1 times 10 to the minus 6. Using your exponent button, I'm going to say that's going to give me 150 micrograms in this case. By the way, significant figure-wise at this point, how many significant figures should that number have? Does it have 3? No, not the way I wrote it. It doesn't have 3, right? It has how many the way I wrote it? And if we add those together, we get 3, which is what we need right there. Yeah. So it actually has 2 the way I wrote it. Now it has 3, right, with the decimal. The reason we need 3, technically speaking, is that's an exact number, right? That's an exact number. Really, this guy had 3 significant figures when we started. Should still have 3 significant figures at this point. Yeah. Any questions? All right. So here's where dimensional analysis still is very helpful. I now know how much I need to give this patient. So I'm going to use my conversion factor that was given to me in the problem. And all it has to remember is opposite, right? So micrograms are on top. Which conversion factor should I use? The one on the left or right? The one on the right is micrograms on the bottom. Yeah. That gives me 50 micrograms per tablet. That is going to get rid of the micrograms, which is really good because we want to know how many to give this guy. And that would technically be 3.0 tablets if we were doing a little significant figures on this, because we should look at this, which is 2 significant figures. That is 3 significant figures. That is 2 significant figures. In this case, if you were calculating a tablet, like I said, you probably want to crush it and give a guy like 0.33. So maybe it might round to a whole number in a book or something like that in a real life situation. But that would be basically, I give the person 3 tablets. We'll leave it at 3.0. That gives us the right sig figs, and it's still a whole number. Question on any of those calculations? All right, we will lay it up here. By the way, that is